In this study, they used 5 racers, 5 RPM levels, and 5 power levels to look at heart rate and VO2, oxygen uptake, during each of these episodes. If you look at the lowest curve, 100 watts, you'll see that at 40 RPM is about the same as 60 RPM, not much difference. Then from there on, the heart rate goes up quite a bit as you jump to 80, 100, and 120 RPM. As you go up to 150, 200, 250, 300, the biggest difference is the change in 40 RPM. And because of that, they fit curves to the data. The bottom of the curve seems to shift to the right because 40 RPM goes up so much faster than the other side of the curve. But in all cases, 60 RPM is the lowest point. I've connected the points with a red line, and you can see very clearly it goes up from 60 to 80, up to 60 to 80 in every case, even at 300 watts. Although it's looking like 60 may be closer to the bottom. But the bottom is probably to the left of 60 in all cases, in terms of pure optimum, where the best place to pedal for heart rate is. And the same was true in the VO2 curve. I think it may be that as you go to 40 RPM at higher power levels, you're having to recruit some fast twitch muscle. The other thing that happens is that at 60 RPM and 300 watts, you're putting 95 pounds of force in the pedals. At 40 RPM, you're having to put 142 pounds of force in the pedals. This is lifting you off the seat. So it may be inefficient because you raise up and then your body weight puts down on the pedal. You may not get as fast an uptake of pressure on the pedal. It may not come in as soon in the cycle, and so it becomes less efficient to ride at that super low RPM. But at 60 RPM, it's still more efficient than at 80. Worth looking at. I'm not the only one whose heart rate goes up at the same power level when I increase my cadence. We've seen that optimum cadence corresponds to the peak of the power curve, which comes from the velocity versus force curve. In this velocity force curve, I've imagined that you could increase your velocity by 20% and your force by 20%. The resultant power curve is an increase of about 40% in power. Now, in reality, I think it's pretty hard to change the velocity of your slow twitch muscle. It works genetically at a more or less predetermined pace, but it's conceivable that some people have higher velocity slow twitch muscle than others. People with high VO2 maxes, natural world-class athletes, probably have much more mitochondria in their slow twitch muscle, which means they can produce much more ATP. They can recycle adenosine diphosphate, which ATP breaks down into, so ADP becomes ATP much more rapidly with that muscle. They have a higher concentration of ATP around their myosin heads within the muscle, and so those myosin heads can move quicker. They react faster. They clear ADP faster and then uptake ATP more quickly. So what we could do is increase the concentration of our mitochondria in our muscles by training. We can increase the efficiency of them. There are certain supplements we can take. CoQ10 is involved in electron transport within the mitochondria, and so that helps prevent oxidation damage, but it also provides the electrons that are used to make ATP out of ADP. Alpha-lipoic acid gets rid of free radicals, which actually bind with the proteins in the mitochondria and make it less efficient, make it work less well. So alpha-lipoic acid will actually regenerate those proteins. It'll take the free radicals off of the proteins. Acetyl L-carnitine helps you import fat into the mitochondria for fat-burning purposes. Shilajit is an Ayurvedic compound that works with CoQ10 to enhance mitochondrial function. And there's something called PQQ that's supposed to help you synthesize mitochondria. Mostly it's training. I think you have to train all your mitochondria and all your slow twitch muscle by using high force. That recruits more of them at once, but also you can train them at higher speed. Anytime you're pushing the limits on them with intervals, whether it's a high force interval or high speed interval, you're going to synthesize more mitochondria after that. To increase force, you can recruit more muscle motor units by shifting to a high gear and pushing hard on the pedals. Then you're using more of the existing muscle that you have. You can also train your muscles with high force pedaling. That's basically you're building more mitochondria in muscles that are rarely used if you ride at higher cadences. Low cadence or riding up a hill at a pretty low cadence, high force, you're going to force the muscles that don't normally get worked to build more mitochondria and be more aerobic. But they're slow twitch muscles, so they would have a lot of capacity for that. And then you could also use super slow weight training. Weight training doesn't work very well for cyclists, but if you're going to use the muscle strength that you have, then weight training should work. It's just that most weight training is aimed at fast twitch muscle. It's a very fast motion. Even the guys who classically push up for 2 seconds and down for 4, that would be a little better, but most people actually it's up 1 second or less and down 1 second or less, and so 8 reps just doesn't, you can't warm up your slow twitch muscle. That takes 40 seconds. So super slow, where you find a weight that you can push 10 seconds up, 10 seconds down for 1.5 to 2.5 minutes to exhaustion, will actually use up the fast twitch muscle, warm up the slow twitch muscle, which again takes about 40 seconds, and then work the slow twitch muscle. And you'll end up having to use a weight that you can lift only with slow twitch muscle, because the fast twitch will have just gone out of the picture. So it may be half, maybe 60% of your max 1 rep max, but it'll work your slow twitch muscle. So these are ways to increase both the force and velocity of your muscles to try and get more power. Changing topics, let's talk about glucose stores in the muscle called glycogen. In this study they took 14 physical education students and gave them the painful procedure of muscle biopsies, needle biopsies, where they stick a needle into the muscle, extract some muscle, count the slow twitch versus fast twitch diet to see how much glycogen is still in the muscle before and after exercise. So they had them ride at 31% of their VO2 max, 64%, 84%, 120, and 150%. I think they're actually aiming for 30, 60, and 90% of their VO2 max, but these are the averages they achieved. The top blue curve is at 31% of VO2 max. They started with about 83. The units on the left are millimole glucose per kilogram of body weight. On the bottom it's minutes. So they started with 83 units of glucose, and after 3 hours of riding they were down to about 44 units of glucose. Very efficient. The magenta curve is 64% of VO2 max, which was a 2-hour experiment, 120 minutes. They started with about 81 units, rapidly decreased to below 50 units in about 20 minutes. At that point it seems that the curve is curving, it's slowing down in terms of the use of glycogen, and ends up from 60 to 120 being pretty much parallel with the glycogen depletion of the 31% people. That's very interesting, and we'll talk about that a little bit more. The yellow curve is 84% of VO2 max. It's a straight line. They rapidly deplete their glycogen right down to 20. They were supposed to go for 75 minutes. They only lasted 60 minutes on average. They were exhausted. When you get down to 20 units of glycogen, its flow rate into the mitochondria to produce ATP is 1/4 of what the flow rate was when it was 80, or it's diminished a great deal in any case. So there's much less ATP flowing back into the myosin heads in the muscle tissues and fibers, and so they just can't sustain that rate any longer and had to quit. What's interesting here is that between 64 and 84, the yellow and the magenta, they're going down at the same rate initially. So they're both just burning glycogen 100%. Their RQ, respiratory quotient, is 1. It's all glycogen burning. But after 20 minutes or so of warm-up, it appears that fat burning is coming into the picture for 64% of VO2 max. Not for 84. 84, that's never going to happen. It's going to be glycogen all the way. But you're starting to burn fat. And what's kind of amazing is that you can ride at 64% of VO2 max and burn only as much glycogen as you're burning at 31% after you're warmed up sufficiently. So a lot of fat burning is going on. The problem is that you've already lost 30 units of glycogen in the first 20 minutes. That implies to me that you need to warm up slowly. If you warm up at 30% for 20-30 minutes and then continue on up to higher 50-64% of VO2 max, you'll have much more endurance, because you won't hit that 20 unit of glucose mark at 2 hours, you'll hit it way out at 5 hours or something like that. Now the two very short, steep curves are 120 and 150% of VO2 max. The turquoise one is 120. They lasted 20 minutes before they shot it all. It's interesting in that it has a very steep curve, and then after about 3 minutes, the curve becomes a little shallower, implying to me that some aerobic capacity is being used as well. But with the 150%, the dark purple curve, it's almost all just straight anaerobic. It goes straight down in 7 minutes, it's all gone. So now we maybe ought to look at the rate curves. This curve shows the actual rates from each of the curves in the last plot. It shows the glycogen depletion rate in millimoles of glucose per minute, so units of glucose. The minutes on the bottom shows the duration of each of the tests that they use. The first peak is the 150% of VO2 max effort, where they start at 6 to 8, back down to about 5 units of glucose per minute. The second one, the turquoise, starts at 7 units of glucose per minute, but then drops down to about 2. Here I interpret that as the addition of aerobic capacity. It takes a few minutes for the aerobic to warm up, and then it's providing some of the energy. The yellow 84% curve starts at 1.4 and goes down to 1. It's all glycogen usage, and they're worn out after an hour. And if you think about that, the average of that 1.2 times 60 minutes is going to be over 70 units of glucose used up, gone. History. The magenta starts at 1.6 units per minute. It's burning glycogen initially only, but after about 20 minutes it's burned a lot of that, and it's starting to warm up the fat burning, we think, and consequently it then diminishes and actually ends up burning just as much glycogen as the 31% group of writing experiment, which is rather amazing, because you'd think it'd be burning more glycogen, and it might be burning more fat as well, but it needs to burn twice as much glycogen and twice as much fat to produce twice as much power. And it's not. It's burning probably a lot more fat and the same amount of glycogen, or so it would appear. The people riding at 31% VO2 max start at 0.3 units of glucose per minute and are down to about 0.15 unit per minute later on. So I guess their fat burnings just continue to get more efficient as they ride along. Now, if you think about Jeff on Sunday morning starting out slowly, then he's preserving. Had he started out at 64%, he'd be burning up a lot of glycogen rapidly, and he's preserving it by riding slowly with the group. It's a social ride. After the first hour, first stop, 14 people go home, 2 or 3 people go on and ride 100 miles. Well, he saved that glycogen for later in the ride. So in the 5th hour of the ride, he's still got plenty of muscle glycogen, muscle glucose to depend on. On the other hand, if you sprint every hill, 20-30 second sprint up every roller, after about 14 of those, you'll probably have spent 7 minutes at max production anaerobic capacity, and you will have depleted all your glycogen. So unless you're sucking down chocolate and milk or slowing down in between, I don't know how you survive. It's interesting to look at. This is all in percentage of VO2 max. Assume that VO2 max is 300 watts here, then 31% is a little under 100 watts, 150% is around 450 watts. So if you divide those by the watts, the glucose units per minute, so let's say we have 450 divided by 8, we'd get 56 watts per unit of glucose in the purple curve with the anaerobic curve. And in the aerobic curve, at its best, we'd be seeing 100 watts divided by 0.15 would be 667 watts per unit of glucose. So 11 to 12 times more watts per unit of glucose by riding aerobically rather than anaerobically. A good use of your muscle glycogen.